All right. Okay. Yeah. So I will try to get through a few things today. So I've been kind of saying that I want to get through or the observation model and cross spectral DCM. So I'm going to start that today, hopefully. Talk to you all about that. But before we do anything, I would just say that this is the last very heavy theoretical kind of workshop thing we're doing. The thing we're missing after all this is the how to generate inference or how to do the Bayesian stuff. We'll go for that just slightly for half a session because all that's under the hood and sort of a lot of that is really kind of unnecessary to get an understanding of all these DCM concepts. That we'll just get sort of some tools if you want to know more about it and how to get started. Okay, so let's talk about the homework from last week. Okay, so we had, again, let's remind ourselves, we had this frog-mosquito system again, where Y is the mosquito, X is the frog. And we had, of course, the frogs eating the mosquitoes, given by this term here. And we have the frogs also, the mosquitoes also dying, given by that term there, sorry. That's the frog term. Then we want to say we actually added some mosquitoes in by the U1 term. And then we actually modulate the rate of change of these frogs eating the mosquitoes because of this input U1. Sorry, modulate input U2. Yeah, that all seems familiar? Okay, now, how many people did it? Some people did it? All right, good. Let's see a hand up for you too, Nigel. Yeah, all right, good. Okay, so does anyone want to attempt to draw it on the board?
Oh,
yeah, is that you?
yeah.
No? Maybe I'll get. Has anyone got a picture of it printed out? No. Alright, it'd be hard to do it, I think. So I will say that the solution. I'll get people to do the next homework problem. It's much easier to actually draw. Okay, so what you should have got, you should have replicated the first one, just on your as of part 1. So part 2, what it should look like. So the mosquito population, how does it look like? You should have gone up high to a value of about 3 or so. Dip down just below 10, up here, and then a kind of delay rate there. That look familiar to people? Yeah? The mosquito population should have done this. Kind of go all the way up to about 6. You check later at home if you want to, and then up top there, and should have decayed down, and a sort of wonky decay down there. Does that look familiar to people? Yeah? No one's going to contest? Yeah? Okay, cool. So the things that we kind of added, we added this input term U1, which is why we had this increase in the frog population and the mosquito population. We had this modulating term here, which we said before, which we're modeling that frogs are eating mosquitoes at a faster rate because of this modulation. So we had this term, this U2 modulation times this term here. Yep. Okay, so what we had here, we had this sort of, as you can see here, this kind of sort of delay that looks not like we had before. What we had before was something more like, I'm going to draw it here. The frogs did this before. Decay term. So it's because of this modulation term. And these things, they look quite qualitatively similar. I mean, I have this figure here. You can see that. And I'll put it also picture in the YouTube link. They look quite similar, but this modulation term changes this decay rate in both terms. So the frogs also have a less increase because there are less mosquitoes, they get eaten quickly. So the frog's greed makes less frogs. This is the outcome of what's happening here. Greedy frogs eating faster because of this time. Because mosquitoes are actually slower, as we modeled. So when you think about this in terms of the context of neural design, if you have this modulation, you can also change things like decay rates and all these things like that. And these terms are what's been modeled in DCM. Yep. All right, good. So the next one, I'm going to get someone to stand up and do parts of it, was the connectivity diagram. Did you all attempt it?
Yes.
Yep. Alright, so if I have this matrix down the wrong way, please remind me and tell me if it is wrong. So for the A matrix, we have the following. We have C. Okay.
I took a photo of it, so I have it as it was.
U equals U1, U2, U3. Yes?
Yes.
We'll call Z. Okay, I'm going to call it now just R1, R2, and R3. Just for convention's sakes. C is equal to 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Everyone had that?
Yeah.
Yeah.
Cool. The next thing we'll do is then put in what A is equal to. Okay. Yes, see the wrong way around. Did I write down the wrong way around or?
No.
No. Okay. So I think let's go through this together. This is important. And like I said, everything is like the most important part. I would say.
Minus 0.5, 0,
And 0.
and then 0.7,
0,
0, minus 1.
Okay, B1 is 0.
Yeah.
I'm going to do B2. That's pretty bad technical use there. Equals.
It was 0, 0, 0, 0, 0, 1, 0, 0, 0.
Okay, now I'll do B3 is equal to
0, 0, 1, and then just all zeros.
all zeros. Okay, let's do this together. Alright, so we're going to have, it'll be a little bit smaller, sorry about that. U1, U2, U3. Okay, I'm going to do like this, R1. I'm going to do like how I have here, just because it's easy for me to look. How it looks like. R1, R2, and R3. We're going to run out of space soon, which is annoying, but okay. Now let's.
And how do you put the regions in that matrix? Can you
That
say
is also right. So
R3, R2,
R1, R2,
R1,
R3. So the way it works is, remember for each of the matrices, this is 2, and this is from. Okay.
Yeah.
So let's look at this one. Let's look at the matrix. That's fine. That's fine. C. So this here is 2. This is here inputs, and that's regions.
Yeah, so they all took region 1 there.
So we just have this one.
Mm-hmm.
Yeah?
Yeah.
Ooh, okay, good. A. So the first one is a self-connection, which is minus 1. So yeah, this one here. This one, this is saying region 2 from 1. Region 2 from 1 is 0.1. Yeah, region 3, because this is row 3 from 1 is 0.7. Okay, cool. Next one. Here, this is column 2, but row 1. So region 1 from 2 is 0.2. This one here, self-connection, 2 onto itself. This one here, nothing's happening. And then this is 0, 0, so region 1 and 2
From
3, there's no connections. And region 3 into 3, it's minus 0.1. Okay, cool. I think it's good we're going for this clarity.
Yeah.
Clarity. Now, sorry I didn't give you the regions by this thing. That's my fault there. Okay, last one here. Second last one, this one. This here, we have second row, which means region 2. We have third column.
From 3.
From 3. So region 2 from 3. I'm going to do it in black. Is this. And I'm going to modulate it. Everyone agree there?
Mm-hmm.
Last one we have here. So we have, what's this one?
Region 1
From 3.
Region 1 from 3. Here. So I have
From Okay.
Yeah,
Let's use the input.
that should be. Okay, so we should be really careful with these because this is a convention that DCM uses, and it's a convention because we use these as column vectors. Okay? Now we had this I had a discussion with someone about this, about directions, and last week we talked about directions as well, so I think we'll go a little bit into that as well now. I have that anyway. Yeah, this is how it all looks like. This is how the home solution looks like. Because I mean, it's almost a little bit under the hood in terms of DCM, how they describe this too, in the first paper. And it becomes clear from the equations that it doesn't have any kind of diagram saying what the indices mean and things. So let's go through that again. I just want to go there as a recap. What the bilinear model is. So, okay. Let's go into that again. Just to recap. I think someone said as well, like, said all this map stuff is quite difficult, I think, if you haven't seen it for a while, first time you've seen it. But being familiar with it, doing it again and again, this is how you can master it, I'd say. Okay. This here is the, what's it called? Someone say it. What's this model called? The bilinear model. They all shout out once. The bilinear model. Okay, so we did this. We went through from the start in the first lecture what this actually means, this differential equation. We then solved the differential equation, very simple frog and mosquito system, and we built up to a more and more complicated model. And then we reframed it into the matrices. And we from scratch went from these simple differential equations, or these simple equations, up into something that looks more complicated, but it all is a different dialect of describing something that we've been going through descriptively. Okay, so A, again, remember just keeping notes and keeping your head here, is a matrix which describes the describes the continuity between regions. This is two regions, and this is from regions. In other words, A of row M and column N, it's the connection to M from N. Okay, this is what the A matrix means. Continuity matrix. It's a directed connectivity matrix, which is very different. B of J equals the same thing. This is from to, and B J of M of N is the modulation of connection to N from M by, so modulation of this connection by input UJ from, yes, so we combine together into one. Yeah. Okay, again as well, last one, C, which is a less interesting one. Well, not really. Well, it's always quite simple. This is from input to region. And C of, I said MN, sorry, M, was, hold on. So, connection to N from input I. This is the bilinear model. This is what all the terms mean. So I'm just repeating what I said last week, just so we kind of all know this, and when you go through DCM and read the papers, you're not scared of this anymore. Is anyone still scared of this? Please tell me. No? Okay, good.
Excuse me, I've got a question.
Yes.
So about the those kind of modulations, when we have the effect on connections, can we have the effect on connections when we don't have any intrinsic interaction between those two regions?
I guess you can really, but you need to have an input which modulates these. So you're saying, can you have...
For example, X and Y do not have any kind of intrinsic interactions within themselves.
Okay.
But how we can have modulations?
I would say you need intrinsic, you need this to be non-zero, just in terms of the dynamical systems. I mean, you can do it. It just would have been different meaning in this context. And in some ways, that's like a very general thing to do. I mean, essentially, all of these have modulations of 1. Yeah. So in a general form, it's right.
So in our example, so we had, for example, X and Y without any interaction, but we had modulation under connections.
So we did have we did have A actually, because if you look in the equations, where you have dy dx is equal to dy dt is equal to x. That's an intrinsic connection. There's no modulation there. And the x dt is equal to minus y. We have an intrinsic one. Oh, you mean in the example for homework?
Yes, in this example. So we don't have anything from
X
to
yes,
Y.
you can have that, yeah. You can have sometimes these things just forming because of a particular task, particular attention task, you have these things interacting.
Something which already is not, doesn't exist.
That's right, yeah. So you might have, for instance, in the visual and spatial networks, you have them kind of operating independently. And when you have an attention task, you can have these sort of visual spatial networks being activated because of this modulation. I know what you mean, yeah. So you can have that kind of stuff happen. In fact, I think in the DCM paper, there might be a connection like that, I think. Let me just check, is there? Yeah, there is, from Z3 to Z2, but that happens. So have a look at that. Good question, good question. Okay, now, we kind of did all of this, and this is now a linear model. We first had a very complicated general model. This was quite simple. And the question is, why does this even work? I mean, if you look at the neural mass models, and Hodgkin-Huxley models, all these more complicated models, they're much more complicated than this. We might have z squareds in some cases, not just these matrices. You might have u squared. You might have z times u all squared times sine of all this kind of stuff. Very complicated equations. Now the question is, why does this actually work for our purposes, and why don't we use anything more complicated? Now I'm going to show you an example of why this works in a neural case to do with membrane potentials. This is a model kind of neural field theory. I'm going to show you a little bit of that and kind of show you why the linear model kind of works. So I'm going to keep that up there. So one thing that's modeled in these neural field equations is the rate of change, or the pulse density change. So I'm going to call it Z. So here in this case, Z is equal to so pulse rate propagation. Okay, and we have thing which is membrane potential. Okay, so an example which is used in these contexts is saying the following. Is saying that the change in this term, of where the pulses affect each other, equals, this rate of change of that term is dependent on Q. Okay. Q is equal to the firing rate of neurons. Okay. Now this looks something complicated. It looks hideous when I write it down. I want you all to be disgusted. No, don't be disgusted. I like this equation, but it's non-linear. B minus C over sigma. Okay. And then we can also say that the change in membrane potential is a very simple neural model. It's people in the field would scream at me because it's not exactly correct, but it's in a smaller version of this. I.e. Peter Robinson, my supervisor, would scream at me right now. Okay, as you can see here, this is not like that, right? We have a division. The v is like on the other side. It's exponential. It's crazy. So if I actually look at this term, what it is, this term here, I'm going to plot like this. dz, dt, and b. This looks like this. Q. So there's a point here, which is that term here, which is the resting membrane potential. You might see this also in many papers. Potential. So it says the rate of change of the pulse density propagation is given by this term here. This depends on the firing rate. Now, what is that? What is this? Let's describe this a little bit further. So, if you might know from your classes in neuroscience, Bunkenville and Schwartz and all this kind of stuff. If you have a neuron, right, and you stick a membrane potential to it, you change the membrane potential, it'll only fire at a certain point. That makes sense, everyone? Everyone knows this stuff? If you have another neuron, which is slightly different, you might see, because it's different size and all that kind of stuff, the membrane potential kind of shifted. It's a little bit different in terms of fires or not. In terms of firing, it's a smaller membrane potential here. And you can see here, different neurons have different type of thresholds and all this kind of stuff. In a population, it looks something like this. Okay? The firing rate, depending on the local sort of potential, looks something like this. It's a distribution. It's no longer like this blocky diagram. Like you figure it's smooth. Does it all make sense now? What this means? You might have seen this, might not have seen this. It's like a key thing in a lot of neural models. Okay. That's the background of what this equation is. So then why if this is so important, why is the linear thing even working? Why are we even using this? Now if we zoom in on this, okay, I'm going to take my whiteboard magnifying glass. That was a joke, you're supposed to laugh at that one. Fine. Laugh at me being self-deprecating instead. Okay, so if you take a look at that, you'll see that it looks like a straight line, doesn't it? It's really, I mean, if you kind of look at, if I look at the resting potential here, it just looks like a straight line. Now the idea is that if your voltage doesn't move very far from this resting potential, you can just approximate a straight line. If your membrane potential goes all the way here, of course you're going to include this entire shape. Does everyone understand that idea? So it's just approximating this curve with something really dumb, a line. But this works in many, many, many cases. You can say something hideously complicated in this rate of change, and you'd approximate it by a line. And that's what the Volterra model does. It makes these, more technical terms, these first order approximations. It's like the dumbest approximation you can make. It's all technical, has all mathematical background, but it's like, if you think about it, it's like a dumb approximation, a first approximation. Okay? So how can we then use this? Now I'm going to show, I'm going to write some stuff down. So while you write down, I'm going to write something on my board myself. Okay, so actually I might write here. This side. Right. Q. So I'm going to call it Q plus B minus. Okay? So as I said, we think it's a straight line. We can just write this And what this is saying, we're saying, okay, what this term equals to is essentially the value at this point plus a little line. What this little line is like, it's a constant factor k, and we're going to call it, you can derive it from first principles, etc. Or we can actually just calculate it yourself, depends on the gradient there, and how far you are from this steady value. Okay? So I've done that trick. And then what I can do, I can just literally write dz dt equals, for first order approximations, q theta, which is a constant value now, times k b minus theta, and then we then still have this last term here. I'll write at the top as well, might be a little bit nicer. So this is what we've done. We've taken this complicated system and we say, remember potential only moves slightly, and this is what we get. We can write the equations like this. And this was very similar to what we had before. You don't have anything squared, anything too crazy. We have linear cases, so V is the only one here, and it looks like almost like our frog system, frog and mosquito system. And this trick can be done for many, many systems. And what we've done here, this formal process is called Taylor expansion. So if you read that in the papers, I mean, mostly all the DCM papers, they talk about a Taylor expansion. This is what a Taylor expansion is. You can apply it to many other models. And just for completeness, if you have a function f, so function f, you want to linearize or approximate about a variable a. Okay? Now I'm just going to write this down. It's going to look really bad, but don't worry, this won't be part of the homework or anything. 1 to infinity df dz. So I just want to show you this, that process, you might see this in the papers, they have it in the appendix, I'm sure, is this term here. So that process we did here, linearization, is called Taylor expansion. It looks like this in the most general form. Okay, it looks really scary, but it's just doing this, making little lines, making little expansions. If you have anything really complicated in your modeling, if you want to model for electrical circuits, electrical conductivity, if you do any source modeling, mana, you'll see they do these as well, these Taylor expansions. They take the full system of electrodynamics, and they do this expansion just to look at something in a resting potential sense, and they'll do something like this for sure in the inverse solutions or that kind of modeling. So this makes any crazy function, it makes it tractable because we just take small chunks of it, more and more approximations. Like, I'll show you again with one, before we move on, just one example. So just what I showed you before, but like in the general case, you can have something like this. A, that's f of z. Okay, so the first order, or 0th order, f of z is approximately literally just f of a. The function and value of it at a. It's just a straight line. That's the really simple case. First order, it's f of z equals f of a plus this term here, which is just like that. Okay. Second order, you have an increase in that thing, and it just ends up being something looking like function looks like this. And of course, if you go to infinity, the more and more things you go, you can approximate this, or you can have this complete reconstruction of this curve. The reason why I bring all this up is just to show you why this works, of course, but also they talk a lot about Volterra series. They talk about this in all DCM papers. And what Volterra series are just Taylor expansions on all the equations. And they put them together to form what's called a Volterra series. So you can take this formalism and actually do the entire modeling and look at this in terms of an expansion. Because unfortunately, so they show all this stuff and they actually show, in the most general case, how to derive this in the Friston, not in the DCM paper, they show you in the appendix of Friston 2000, that balloon model paper, the one Marina has there, in the appendix, and they never kind of show it ever again. They just refer to this paper. But they can't really explain what it is. This is what it is. This is a bit heavy, this part, I know. But just exposure, if you hear this again, then you'll kind of know what all this stuff means. Alrighty. Okay, now after we have this, we describe almost everything on the DCM model. Okay, we've described oscillations, we've described decay, we've described differential systems, bilinear model, what does connections mean in terms of the neural model. So I'm going to show you in a diagram here what we've done and what's left. Okay. So we've had, why do I keep changing this pen? It sounds terrible. I'll put it here. So we have inputs. So there are U1, U2, U3. We then have, here we have the Z. About this time here. They're also called hidden variables in DCM. And most of these input-output functions, models, should say. The last one here is the observation model. Or I'll call it the observation, maybe. The observation model. This is the last thing we haven't discussed yet. I just want to go through it, but not too much in detail. So what this observation model is, it can be anything. It can be EEG. So you can take all these hidden variables and determine what an EEG signal looks like from these functions. It's tiny more complicated with this, but it's a general idea. You can add MEG, ECOG, nerves observation models to make observations, or you can do the classic one. The first one is the fMRI, or the hemodynamic response model. And that's what is in that first paper, and that's what we'll kind of go through a little bit now. So these are models. Like I said before, you do the inputs, you calculate hidden variables, do the observation, compare to your data, and then update your model. And you do it until you converge, until you have the inputs, so you have all the parameters optimized. Okay, cool. Okay, so that model is called the hemodynamic model, and they use something called the balloon Wing-Kessel model. So I might get excited by this, talk about this, because this is more my expertise, and all this stuff is about I'm probably most confident at. Okay, so the balloon model, what it is. So we want to actually model the bold response. So things we have to know about the bold response. So if you're in bold kind of bold imaging, you might know a couple of things here. So things or tenets we have, we know. So when neurons, when they fire, okay, or when they're quite active, we know they strip away oxygen. They strip oxygen from strip O2 from DHP. Okay. So they strip. We don't know the entire mechanism for this, but we kind of know this happens. They strip O2 and also gets fed into neurons, into glia. Okay. Now, we also know to meet demand, we know that blood flow increases. The blood flow increases. Okay? I think we also know. We also know the following. So we know DHB, so deoxygenated hemoglobin in blood, going through blood, that causes the bold contrast, it causes the bold to go down. It makes the bold response go down. We know that OHB, oxygenated hemoglobin, actually increases the signal contrast and makes bold go up. And this is quite an interesting thing. We have these neurons, they are of course are more active, they strip more oxygen. But you'd expect like the contrast to go up, but in fact it does the opposite. It makes the bold response go down. The reason why bold increases after activation is because the massive inflow of blood flow, and that blood inflow has a lot of oxygenated hemoglobin. That's what happens in bold response. Okay, so these are the things that happen in terms of the balloon model, and we have to model. So all hemodynamic models have these requirements they have to fit. So I'm going to go through the balloon model now, and I'm going to go through it quite quickly and just descriptively, and I'll show the equations as well. So the balloon model does this, the REST delay compliance model by Mandeville. Another model does this, the REST model, which has the prompt arterial dilation model, and the spectral hemodynamic model, which is the model I helped develop. Okay, so let's now go to some equations now. And all we have to do is we're going to go through them quickly and just show some points and bits and pieces, and I'll kind of test your skills. This is essentially the in-house work. So we're going to have to model the following variables. We're going to have V equals venous volume. Okay. We will have S as a vasodilatory signal. Okay. We're going to have F, which is blood flow. We're also going to have Q, which is the DHB content, concentration, and Y equals bold. I also added, this is specifically modeling the changes in the veins. This is what the balloon model is looking at. And one idea they had was that possibly as you increase blood flow, the venous inflates towards the balloon, gets bigger, and slowly deflates. These are the physiological principles behind the balloon model, which is why it's called a balloon model. And you find this ballooning in kind of in some of the respiratory system. That's where it comes from, this sort of modeling. Okay, now I'm going to go through these things. So what they say in the model that the rate of change of blood flow is caused by the vasodilatory signal. So somehow neurons say, okay, increase blood flow. The rate of change is equal to this. Okay. Hope this is not scary now that we've gone through differential equations. Yep. Good. That's my whole point here, that you're accustomed to this and to wanting more maybe. Probably not. Probably not.
How do you measure the S? Like how it's measured, how it's evaluated?
This is a very, very good question. This S, we're going to model now, but the the signal that increases blood flow, which is I guess called the neurovascular coupling problem, is very well debated. S can be cause of neurotransmitters, can just affect the end feet of the arterioles and make them kind of change calcium channels and inflate. S can also be from glia, which also sends signals to the arteries and change the increases in blood flow. It can be a combination of the two things together as well. There's many different pathways to cause blood flow change. So it's a hot debate. If you go to like Society for Neuroscience, there's like symposia on the neurovascular coupling problem. So it's so Carl Frisson in 2000, he added this stuff to the balloon model, which wasn't there before, and he has this simple system. So he says that the S changes in this way. So he says you have an increase of neuroactivity. Oh, sorry. We'll call it Z, as we called it before. Sorry.
What is the first sign before Z?
This is a parameter, which is E. Or, yeah, little E. Okay, then we have minus F minus 1. And one thing I'll note, just don't worry about these constants that I haven't thought about, these ones. Just the constants there. That's TS. So I'll also say that all these are all normalized. None of these have units. So 1 means venous volume, so it's most maximum. F of 1 means most maximum blood flow. Or sorry, resting blood flow and resting venous volume, sorry. Okay, so this is the two equations which describe the change in neuroactivity, neural drive we'll call this. This changes this vasodilatory signal which drives changes in blood flow. Okay, now I'm going to ask some questions. Okay, we have a couple things. We have two variables. We have them kind of swapping here. Okay, we also have negatives in front of them. What kind of behavior do you expect in this type of model? I'll give you a hint. We did some of these behaviors in the previous and the one before lecture. What's that?
Decreasing both. So
Yeah, good. We have a decrease here.
and then consequent here.
Yeah, so we have the state-dependent term here. Better decay. Good. That's one big thing. Awesome. We also have decrease in this due to blood flow. We're saying so. What this actually says, the rate of change of the vasodilatory signal, okay, it becomes less if you have more and more blood flow. That's why it's a minus in front of there. So what it's saying is that if you have enough blood flow, your demand for this, your rate of change, decrease goes to 0. That's what it says. So we have decay. Good. What else should we have here? What other behaviors do you think we should have? Starts with O.
Oscillation.
Yeah! Because we have coupling. See, that S is here, and that F is there. We have coupling. Okay? And what I said before, the kind of the main things we have is oscillations, exponential decay, and kind of constant stuff, neural drives, and that's what we have here. Things put it before, that's present in this model. It's a realistic model. Okay, the next terms are, so yeah, I'm going to just write here, so we have oscillations and decay. Okay. The next terms, I'm going to write out for clarity. This is gone now too, Jesus. Of course, 1 on tall, F in minus F out, B and F out. So this is now a nonlinear function. It's no longer like we had before. These two are linear. This one is nonlinear now. And the last one is the change in DHB. dq dt equals, again, 1 on 4 F. So I'm going to just go through what these terms mean just for clarity and just because I think we just understand just briefly what the model is doing. So that's a comma here. And it's just the model that's using DCM, full observation model. So you can have literally any neural input you want to do another study. You can actually just put it here and solve it yourself when you have an observation model for bold.
What is E?
E? This one E?
In F in E.
Ah, yeah, it's another E, yeah. So
So that's the same E as before.
Different E.
Yeah, different E.
Different E, yeah.
Whatever.
Yeah. So this technically is an epsilon, and that's an E.
And what does the E mean?
Okay.
Is that a constant or that's a measure of something?
This is now a function. It's like F.
Here it begins.
Here it begins. I didn't want to write anything there. It's F and V. This is also non-linear. This is actually crazier than this term here. So I just want to go through what this is. All right. So what this is the change in venous volume. Okay, is at your volume you have a conservation. Whatever goes in has to go out. Okay, this is what it's actually giving you a mass conservation model. It's saying that the actual volume change you have a blood flow in, you take away F out, and it goes in this way. And what this actually says is if you have an increase in blood volume like this F out, because it has this term, it means it'll decay very, very slowly. If you have enough flow in, you'll turn to a balloon or start like a balloon and decrease back down. This here is the balloon of a balloon model. Last term here, the rate of change of DHB. Okay, you have two things here. You have this term which is positive, as you can see, yeah. And this thing is negative. Is that okay to everyone? So positive means it increases the rate. So it increases this term, Q. You all happy with that? Now what this says it generates, this term means it generates DHB by this function here, these things here. It tells you how much DHB generates because oxygen is stripped. As oxygen is stripped, it makes more and more of this. That's what that tells you, the generation of DHB is here. And this last term here, it's minus F out times Q on V. That just tells you the rate of change of DHB leaving the system. Because of course, when you have new blood, it gets pushed out the old blood, which is deoxygenated, kind of goes back to your heart, which then goes to your lungs and kind of takes the carbon dioxide out and makes new blood again, makes it oxygenated again. Okay, this tells you, it's giving you the rate of it leaving this vein system. As it leaves the veins, it goes up through into your arachnoid, which then goes back down to your heart, all that kind of fun stuff. That's what it says. You have for the balloon model, you have an increase in neuroactivity Z. It causes an increase in blood flow. Okay. Then you have a rate of change of increase in this ballooning effect in volume, and you have a change due to a change of GHB due to these processes happening. Okay.
Don't do anything with Y.
Sorry.
So you don't do anything with Y with the bold?
Yeah. So bold is a contrast between. Can be seen as a contrast between Q and V. Because these two have different magnetic properties. So at the end, there's a last model which I won't show you because it's which they call it lambda Q and V. So this last model, which I won't show you, which is just written by that, just takes all these, translates them into the magnetic properties, and using some physics, which is not shown in this in any of the papers I've written, but in earlier papers, how you translate changes in these magnetic fields give rise to the change in your bold response, bold contrast. Cool. That's the balloon model. That's all that is there. And now, hopefully, really hope that having the experience differential equation makes you that more palatable, makes it more palatable. You'd be like, okay, there's some rate of change, increases, decreases, all that kind of stuff. If you can't solve it yourself, at least you understand various parts of it. All putting that together. How does this look like?
Do you all, sorry,
Yeah, go on,
it's a very
sorry.
silly question.
Yeah,
Do
no,
all
go
your variables or your inputs, they are in your model, for example, df, is your variable or is your input?
So the input is just a z term.
Just as that.
Yeah, so that's a good point. I try to write that out, but I'll just say it like this way. So what happens is you're only inputting during activity, and then the system responds, which we're modeling, by changing V, S, F, Q, and Y. Your only input is one thing. In here, you had multiple inputs, is by the new model. Here we just have one input and we get one output.
Which is the hidden state variable.
Yeah, so all these things in between, these ones here, you can call them hidden variables. That's a good point. They're hidden variables because we don't actually measure them in bold. We can only see Y, the bold response.
So if we see Y, the Z, how would Z look? Like what's actually going into the model?
This is good as well. So what is Z? Another hotly contested what it is. But you can do various things. You can do some things which actually work, which is all good. So you can actually have like a task, right? If you have a task which has a flashing checkerboard, big flash, you can model like this. You can say turns on, goes on, and turns off. That can be your Z. Okay? That can be a very simple Z. Now this Z is like, again, you can think about it as like a first order approximation. But if you went to look at what your EEG signal would look like using all these models using this simple Z, it's not right. Z is more complicated, of course. You have innovation for different areas, you have feedback, all this kind of stuff. It probably looks more like, sort of like, something like that. Okay? But don't worry about that. So the question is what to put input as Z. Okay, the input, you can either choose things like the local field potential. You can think about multi-unit activity. Now what that Z actually is, again, people also fight over this like crazy, what is Z? And this sort of idea. But for our purposes, in a simple case for us modeling, we can model it just by something like this. In a case we have a flashing checkerboard. Okay?
So you measure Y,
Yes.
and you sort of make up
That's
Z.
right. Yeah.
Okay.
Yeah. So you make up Z. Or you can also say you can make up different Zs on this sort of model, because you can sometimes know what Z will be in one area, like visual cortex. Very easy in V1. But then the other areas, what they look like, they look something different. And this model will give you a prediction for what that Z would look like in region B or D. Good question. That's all part of this modeling sphere, really. You make predictions. Now, okay, now I will show you now what they all look like. So once we had Z as the input. Okay, flow, I'm just going to show what F looks like. F looks like this. Okay. So your change in blood flow increases and decreases and goes back to oscillation, go back to baseline. Next one, we have, you could think of Q and B. What happens here? So we have the balloon effect. We have, for V, like this, we have an increase in blood volume and then decrease like this. We have this balloon effect. It gets bigger, this venous volume, and decreases down really, really slowly over time. What does Q look like? Well, like I said before, we have this sort of counterintuitive thing that we actually have a decrease term here. Well, I'll put a negative Q there. The Q decreases. And so actually, when you do the bulk signal, the observation model Y is equal to Q, and V. In this observation model, Q is actually negative. So because it decreases, it has an opposite effect. It then increases the bolt response because it's a negative in front of that. But anyway, that's just a side point, you don't have to worry about that. The last bit at the end is what does the bolt response look like? So Z as an input, our blood flow looks like this, on oscillation, decay. V is also almost like an oscillation with decay. Q is also the same. And then Y looks like this. And it all looks quite similar, doesn't it? So one thing I'll bring your attention from this, just before we go on, is that these all look like the systems we already did, didn't we? It looks like the frog and mosquito system, like this thing here. This looks like nothing more complicated. We had those crazy nonlinearities in this equation here. We saw them all like ridiculously complicated. This will tell you straight away from this analysis, if you simulate this, that the system is approximately linear. So I don't really know why it has to be so complicated in the DCM. There are some nonlinearities that can occur, but this can be well approximated by a linear model, which I definitely think so. And this is the observation model. This is exactly everything that happens in the DCM. You have this Z from all this term here. You put it through your model, and this is your observation at the end. So what you normally have, as like Arena asked before, you do a measurement, and you kind of have something like that. And then inside all these parameters, inside all this equation, you have these parameters. We try to vary it so it fits that. That's what we do. And those parameters are all the parameters, these intrinsic ones, the decay time, the different coupling, the oscillation frequency, all that kind of stuff, which is all in there. And also A's and B's. They're also influencing. They also change your net response at the end. Okay, now this has gone to 1 hour and 5. I wanted to show spectral DCM, but I haven't shown it yet. That's okay. That is okay. The last bit is actually the bit that will require a computer. So I think next week, if you have a laptop or something, we can do it all together, and it'll be a tiny bit on the ball. But I think it's better if we just all do things and type things in together. We'll do sequels and stuff, and I'll share some code onto GitHub. So before next week, I'll upload this to my Git, give you all the link in the email, and we'll go together and we'll kind of type these things together. We'll do more hands-on sort of this stuff, more onto this. And we're going to look at the following. We're going to look at the Fourier transform. We're going to look at what coherence is. We're going to look at cross spectrum and cross correlation. Okay, so if any of you don't have an experience with any of those terms, I suggest just read off on a wiki page or even go into MATLAB and see what they are. It'll be a very hands-on next lecture. I have some theoretical notes, which I wasn't going to go through today, but I think it's better if we do like a mixture between the two. We kind of show stuff on the board and like put it together what it all means. But that concludes all of the hardcore theory of DCM in terms of the modeling dynamical side. We went from a simple model to bilinear model and the observation model at the end. Cool. There's no homework this week. The only thing is just to make sure you have a GitHub account. Please have a GitHub account. If you haven't got a laptop either, we'll share it between two. I don't know how many of you have laptops or not. I think you all have laptops, right? Yeah. I can bring my old laptop if you need a laptop as well. And yeah, and hope you enjoyed that. It was, I guess, a bit heavy as well, like all of them have been. But like I said, this is just exposure. When you see it next time, you'll be like, okay, it's not too crazy. It's just complicated away. Another diet is saying something that might be a bit more simple. All right. Yes, questions?
I understand, but so you take the bolt activity, so you measure bolt to estimate the Z, and then use Z to put in the model to predict bolt. First time to do this?
So in DCM setting, not really, almost. So what you do So we can talk about this. Is now getting towards the practical side. What do you do? So you normally have a task. Let's say you have a task which is like flash and checkerboard. It's on, off. Okay. We then have, we'll call this U. Okay. And we can say the U stimulus is on then, off then, and it's on then. And this is our not Z, but this is our U function. Yeah. And this now gets input into all this. And we measure, let's say we measure, this is visual cortex, so let's say we measure in V1. We measure something like this. Probably something like that. Looks crazy, doesn't it? Go sideways. Okay. Alright, that's bold. It's a very simple system. Okay. We also might know that we have V1, V2, let's just say when we have IPS. That's what our U1 is. And we have these connections, right? We assume these connections. Okay? And then we look at the bold response in each of them. First of all, we have all these connections. We put all these connections together into this one here. And then we make a Z for each of them. That will have a Z, that will have a Z, that will have a Z. And then these Zs will get put into the observation model, and they'll get into here. And then we kind of look at this, assess, and then we have the optimization strategy to change all these variables in there. That's the hands-on what DCM does.
But basically, you just think that your Z looks like something. You don't really know, right? You assume that your Z in V1 looks like this.
Yeah, so this term here is just for a case where I don't have DCM, I just have like a simple thing. But in the case, that's definitely true. You assume it. You take the best guess you get, which is just on-off. It's the best guess you have. In this case here, your input is here, and then your Zs are generated by coupling oscillations, all that kind of stuff. So it's like a more advanced version of this.
So
you say it's a model, right?
So it's unfortunately I've done two things here at once, which is what the confusion is. This here is just purely looking at just V1 on its own, no DCM, and I've just got a Z. So in this case, U equals Z.
Okay.
That's about a better way to say it.
But over
Your
there,
input here.
Z is the hidden neural variables in DCM.
Okay.
Yeah, that's right, yeah. That's right. So these hidden variables can become more and more complicated the more and more physiology you put into it.
And then it's the parameters between Z, which are the directed connectivity.
Exactly right. These connections, these things. So you have all this thing, and then you try to change these. You vary these, then this thing gets fit the best. Yeah. So that's, I mean, if you're going to talk about DCM, they'll say this, then they'll say this, and they'll stop there anymore. These are other things that are happening in between. And so the question as well is, like I said, you kind of assume how these work by this model, and it's quite simple. For bold activity, it can be quite simple because bold is very, very slow. Okay, and as I showed you before, the bold response to this is like this. It's very, very slow, which means if you had, so this is your Z if you had that, your U if you had that. If I did this, okay, like that, because it's so slow, because all the parameters and the equations, the bold response predicted bold response will also look like this. It will look very, very similar. It'd be maybe like that different or something crazy like that. Because it's so slow and sluggish.
Doesn't matter if you're imprecise.
Yeah, your neural model can be really sluggish and can be quite simple as well. If you're doing EEG, this will become different. more complicated, but the philosophy is the same. Or MEG, or ECOG, or NERS maybe as well. Yeah, so being sluggish helps for this modeling a lot. It helps. Yeah. I will say though, one thing, I'm going to stick my foot in it here, is that I don't believe the balloon model. The reason, okay, so the balloon model works, it gives you an output, and it can be quite accurate, okay? But the hidden variables have been measured in animals, and the hidden variables look different. So this is why the balloon model, I think, in general, is sort of like dead in the pan. But it still has accurate predictions because the output looks very convincing.
So the bold is right, but the steps in between are wrong.
Exactly, hidden variables. Like this as well, if you actually look at the hidden variables in this sluggish model, they might not look so similar to what you find in neuroactivity.
So then how does it get an accurate bold prediction if it's getting everything in between wrong?
Well,
It's a chance.
no, by
Nobody-
chance.
nobody knows?
Lucky.
Or is it just so slow and imprecise that it doesn't matter?
Well, actually, so when I say, this is me being very picky, and I've been, there's a lot of fights in this field, is because it's just it's almost like the names are wrong. The vein doesn't balloon. The arteries look like they get bigger and smaller, almost like a balloon. Like if you took you kind of look fuzzy, you go, oh, it's a balloon, but it's not actually a balloon. So it's actually largely driven by the arteries do this stuff. And the veins have the biggest contribution of DHB, but the arteries have a much larger contribution than previously thought. So in fact, it almost looks the same if you change the names instead of vein volume to
So it
arterial
should not be
volume.
very important. So hidden variables
tell
should
him
not be.
that.
Yeah. When you get the result, it's okay. So
Yeah, it's a hidden variable, it's hidden.
yeah.
So this is why it still works. It's sort of by chance, but also because other things look like that.
Can you make predictions?
From this, you can.
You mean like you input one variable, you get parameters, and then you like change the task, modify the task,
Exactly.
and that'll give you.
Yes, you can make
You
predictions.
get the point otherwise.
Yeah, exactly, yeah. This is what it does. It gives you these predictions. And you believe a whole bunch of stuff. So things you can do is like, what's this here? So the predictions you can make are things like, you have to write this down if you don't want to, but like if you had two stimuli, what does a bold response look like? You can actually go in an experiment to see it, and you can see things like it's the double hump sort of thing happening. Or depending on how spaced these are, this becomes something like that, all that kind of stuff. You can make these predictions. You can also do things like a priori find out what's the best spacing to get the highest bold signal. So it's something we should do, yeah, philosophy is you use these things not just to fit data, but to make predictions. And be bold and saying, this is what it looks like. Let's use a pun, bold. But you know, this is what you should do with models. Yeah. Cool, I think I've gone over time, it's 4:20. But hopefully that was useful.
It's very useful. Thank
So
you.
next week, yeah, bring your laptop, go on GitHub, we'll have some pen and paper, which might be good or bad, I don't know. We'll see how it turns out. Yeah. Thank you.
Thanks,
Thanks,
Kevin.
Kev.
Woo-hoo.
Thanks, Kev.
No worries.